Hello, in Chapter 9 for General Biology 1, we're discussing the topic of photosynthesis. This photosynthesis is going to be the process of converting light energy into chemical bond energy in carbohydrates. And this is a source of energy for almost all life on Earth. Now, we can classify organisms based on how they obtain carbon. And we've got these two terms of autotrophs and heterotrophs. An autotroph is able to convert inorganic carbon, such as carbon dioxide, into organic carbon, such as glucose sugar. Heterotrophs have to obtain their carbon as organic carbon, such as glucose sugar, but we have to obtain it from some other organism. So, we being humans would be heterotrophs. We obtain our carbon by consuming the organic molecules from another organism. Plants would be autotrophs. Okay. Now then, in addition to classifying organisms based on how they obtain their carbon, we can look at classifying organisms based on how they obtain their energy. And we've got the two terms of phototrophs and chemotrophs. So, photo refers to light, chemo refers to some type of chemical substance. So, plants are phototrophs. They are going to obtain their energy from light. Humans would be chemotrophs. We obtain our energy from chemical compounds. In our case, it's going to be from organic chemical compounds. There are some bacteria that are able to obtain their energy from inorganic chemical compounds. They would still be chemotrophs. The next thing we need to look at in relation to photosynthesis is the nature of light. So the sun gives off a wide range of what's called electromagnetic energy. And electromagnetic energy is energy that can travel through the near vacuum of space, as opposed to something like sound, which has to have a medium through which it travels. So the electromagnetic energy is able to make its way from the sun to the earth. And this electromagnetic energy consists of photons that are going to travel in waves. Now, right here, a photon, you can think of a photon as sort of a small pulse of energy. It's sometimes described as being a unit of energy that has certain characteristics that are somewhat particle-like. And then these pulses, or these units of energy, are going to travel in waves, and the short wavelengths, photons traveling in very short wavelengths, tend to have high energy. Those photons traveling in long wavelengths tend to have less energy. So if we look at this diagram right here, you notice up here at the red end of the light spectrum, we tend to have longer wavelengths, 760 nanometers in length, from the peak of one wave to the peak of another wave. Down here at the other end of the visible spectrum, we tend to have shorter waves, so about 380 nanometers from the peak of one wave to the peak of another wave. So the shorter wavelengths have more energy, longer wavelengths have less energy. Now you can also see that by looking over here at this other part of the chart. Ultraviolet light has shorter wavelengths than what we have with visible light, and we always hear about ultraviolet light in terms of health recommendations, warnings about the dangers of ultraviolet light and skin cancer. Ultraviolet light, being shorter wavelengths, can penetrate through your skin to deeper levels and damage the DNA, setting up skin cancer. If we go to another unit right here, X-rays, still shorter wavelengths, higher energy, and the X-rays are capable of passing all the way through the soft tissues, being blocked by more dense tissues such as bone. So, long wavelengths, less energy, shorter wavelengths, more energy. Okay. So, this visible light, as we saw in the previous diagram, visible light is just a small portion of the energy coming off the sun. We have energy that's longer than, that travels in wavelengths longer than visible light. We have energy coming off the sun that travels in wavelengths shorter than visible light. As it turns out, the wavelengths that are shorter than visible light tend to be blocked by the ozone, a thin layer of O(3) that surrounds the Earth at the very top of our atmosphere. The wavelengths that are longer than visible light tend to be blocked from reaching the surface of the Earth by carbon dioxide and water vapor in our atmosphere. So, as it turns out, the bulk of the energy coming from the sun that can make its way to the surface of the Earth is just a small portion right here known as visible light. We get a little bit of infrared light making its way to the surface of the Earth, a little bit of ultraviolet light, but for the most part, these wavelengths, both longer and wavelengths shorter than visible light, are blocked by our atmosphere from being able to reach the surface of the Earth. Okay, so here we see in this diagram we have the sun and then just a wide array of different wavelengths of energy that are coming off of the sun, and many of those wavelengths are going to be blocked by our atmosphere and never reach the surface of the Earth. It's primarily visible light that reaches the surface of the Earth. Now then, what might seem a bit unusual at first, but in a way it shouldn't, is the fact that the very same wavelengths of energy that stimulate photosynthesis also stimulate vision. So two very different processes that depend on light, photosynthesis and vision. But it makes sense that both of these processes would depend on the same wavelengths of light, because if you notice in item number 1 right there, the visible light is the main form of energy that reaches the surface of the Earth. The other forms of energy, longer and shorter wavelengths in visible light, don't really make it to the surface of the Earth. So, visible light is what we have to work with here at the surface of the Earth. And item number 2, the reason that photosynthesis and vision are both dependent on these same wavelengths of light is the fact that they both utilize organic molecules, and wavelengths shorter than visible light would allow for damage to the organic molecules. Wavelengths that are longer than visible light would not have sufficient energy to stimulate these organic molecules. So, the same wavelengths of energy stimulate some very different processes, such as photosynthesis and vision. Now, if we look at the effect of light on atoms and electrons, in other words, what happens when light strikes some type of material here on the surface of the Earth? Well, light energy causes the electrons to gain energy, and these electrons start moving faster and faster until they move to an orbit, or that is a shell, further from the nucleus. Now think about this in terms of spinning a small weight on a string over the top of your head. If you're spinning that weight in a little circle about 1 foot in diameter, you don't have to do a lot of work to keep that weight spinning in a circle about 1 foot in diameter. But if you want to spin that weight in a circle, say 5 feet in diameter, then you really have to put some effort into that and keep that weight moving on the end of that long string. There's more energy involved. Same way, when these electrons gain energy, they're going to get to moving faster and faster, and they're going to move to orbits further out from the nucleus. It requires more energy to maintain that orbit further out from the nucleus. Okay? So, this electron with the higher energy can do one of two things. It can either fall back to its original position in the structure of the atom, that is to an orbital or to a shell closer to the nucleus, and that energy that it gained will be given off as, right here, as heat. Whoops, let's go back here. Okay, be given off as heat. So, you notice during the summer, concrete, asphalt, metal setting out in the hot sunshine gets hot as it sits there and soaks up that heat energy. Even water in a mud puddle, water in the swimming pool. As summer goes by, it warms up because it is picking up energy from the light. The other option is right down here. There are a few materials that, rather than emitting that energy that they gained in the form of heat, will emit that energy in form of wavelengths of light that are slightly longer than the wavelengths of light that were absorbed. This is termed fluorescence. And so a lot of you have probably had fluorescent stickers that you could stick up on the wall, stick up on the ceiling, and you don't notice them when the light's on. You turn the lights off and they sit there and glow in the dark for a while. They have absorbed the light energy and they've gotten the electrons to moving faster, and the electrons are boosted to higher orbits. Then as the electrons fall back to those original orbits, it gives off that energy in the form of light. Now, with photosynthesis, we have one more option that's available. And that is, rather than this high energy electron falling back to its original position and giving off that energy as heat, which most materials do, or giving off that energy as light, which a few materials will do, in the process of photosynthesis, this high energy electron can be picked up by an electron acceptor. So, as you notice in the notes there, it's another molecule that has the ability to accept this electron, and then it will carry that high energy electron off down a metabolic pathway, leading to the production of ATP and then the production of carbohydrates. This is what happens in photosynthesis. Okay. So, you notice right here, here's our light coming in, represented by the yellow wavy line right there. The light strikes the electrons, get the electrons to moving faster and faster and faster. The electrons are boosted to an orbit further out from the nucleus, and then in things like metal, concrete, asphalt, water, the electron falls back to its original position and the energy is given off as heat. In process of photosynthesis, this electron that has been boosted to an orbit further from the nucleus now has more energy than what it originally had, having gained that energy from light. This electron can be picked up by an electron acceptor and carried off down the metabolic pathway that leads to the production of ATP and then ultimately carbohydrates. Okay, so we're going to stop here on this particular set of explanations for photosynthesis. Hopefully this made sense. We'll pick up with the next topic on the next YouTube. Thank you. Goodbye.